today grade 11. So in the next 2 weeks, as you accomplish all the readings and activities, you will be able to demonstrate understanding of the energy changes in chemical reactions. And at the end of this learning module, you are expected to explain the first law of thermodynamics, compute for calorimetric data using heat capacity and specific heat, and relate concepts of energy changes to practical applications. And for the let's prepare part, you are expected to search for a problem set, just like in module 3 of quarter 3. But this time, your focus will be on work, heat, internal energy, heat capacity, and specific heat. You are expected to present it in GRESA method, show the given required working equation, solution, and answer. Also include the strategy or analysis to solve the problems. As you go along the module, you will understand what this strategy means. And then write 5 to 7 sentences explaining the practical application of your sample problem. Include information such as by the system, exothermic, on the system, endothermic, heat loss, or heat gain, whichever is applicable. And then you may use the last page of this module or write it in a separate paper, or you may have it printed. And lastly, practice orderliness, cleanliness, and avoid erasures. Again, still target for the highest possible score, which is 30 points. And then this is the suggested dates wherein you can accomplish your module. So for activity 1, this is a review of energy calculations. So I put a tip on how you will solve the problem. So for number 1, the tip is to derive mass from density formula. And from there, you may use the heat formula. And then for letter B, it's a direct substitution of our heat formula. For number 2, letter A, you will derive the formula of specific heat from the heat formula. And then for letter B, look for the final temperature. We know that delta T in heat formula is temperature of final minus temperature of initial. Then readings 1 is about energy transformation and energy conservation. So as we all know, energy forms of energy are not all equally useful. What is now the solution for us to maximize this transformation of energy? So the first and foremost constraint on energy transformation is the total energy must be conserved. So how do we do that? First, we must specify precisely what is being studied. Then, which is the system. Then the remainder of the universe is referred to as the surroundings. And this definition assures that the total system plus the surroundings must equal the universe. And then in most cases, the main requirement is that we should be consistent in identifying what is the system and what is the surrounding. we already understand that heat and work are forms of energy transfer, and the overall change in energy is now we know that we designate as E. This is the new term for our overall change. So we can now write it as delta E is equal to Q plus W. So this equation is, as mentioned here, deceptively simple because there is already an addition since, as mentioned, we should conserve energy. So all energies or forms of energy is just added up. But we must take note of the signs or the conventions of these forms of energy. So again, the key is to choose consistent definition for those signs. So transferred into a system is given a positive sign, and energy flowing out of a system carries a negative sign. Thus, when heat flows into a system from the surroundings, Q is positive. And when work is done on the system, the value of W is also positive. Then, heat that flows out of the system or work is done by the system, they are now negative. So, for example, if 515 joules of heat is added to a gas that does 218 joules of work as a result, what is the change in the energy of the system? First is to identify which is the system. So, gas is our system. It is mentioned in the problem that heat is added to a gas. Therefore, heat is added to the system. And then, thus, 218 joules of work. The work is done by the system. So, this is the strategy I am pertaining to the module assessment. So, we must determine the direction of each process. So, this is the direction. Heat is added to a gas, thus 218 of work. So, heat added to the system means Q is positive. Work done by the system means negative value. Substituting the signs of Q and W, we now have 515 joules plus negative 218 joules is equal to positive 297. Take note of the sign of the work. So, it may seem a simple numerical computation, but please consider the signs of Q and W carefully. Always double check. Now, as mentioned in the conservation of energy, delta E should be equal to 0. But in the example, delta E is not 0. So to be able to get a delta E which is equal to 0, we will equate delta E of surrounding is equal to negative delta E of the system. Why? This change in the internal energy of the system is precisely offset by a change in the surrounding. It means that if there is a change in the system, there will be a change in the surrounding. So this is to be able to follow the law of conservation of energy. So it means delta E of the universe is equal to delta E of surroundings plus delta E of system. We can now equate it to 0. This energy conservation is also known as our first law of thermodynamics, which states that energy can be transferred from one form to another, but cannot be created or destroyed. So the next example is an application of is another application of the example of delta E is equal to Q plus W. Again, please take note of the directions of the heat and work. For activity 2, we have two problems to solve, and this is an application of the delta E or relating delta E, Q, and W through the first law of thermodynamics. And then for readings 3, this is another way of computing or solving for heat using heat capacity and specific heat. As mentioned, making the connection between global scale and systems we can observe in a laboratory requires a systematic way to measure energy flow. We can do this by observing heat flow into or out of a system through an set of techniques collectively called calorimetry. So we have two options for expressing the amount of material. All know that it's either by mass or by moles. But either of choice leads to a usable equation in computing heat. So the first is specific heat capacity or the C, usually simply called the specific heat. So this is by mass. If you are given a specific heat capacity, you will use the mass of the material. But in molar heat capacity, as mentioned in the name, is a physical property that describes how much heat is required to raise a temperature of 1 mole of a substance by a 1 degree Celsius. So you will be using the number of moles of materials, which is given by this formula. So either equation provides the same information about the heat needed to produce a given change in temperature. And then below table provides specific heats and molar heat capacities for a few materials or common materials or substances. So as you work through these examples, notice that the heat capacity will have the same numerical value, whether the temperature is expressed in Kelvin or in degrees Celsius. It is because it is not the temperature itself that gives factor to the specific heat or molar heat capacity, but the temperature difference. So, and then this is an example. So, understand and analyze so that you will be able to answer the next activity. And then activity 4, you may use this page for your module assessment part. For inquiries and clarification, please send me a message so that I may clarify your questions. Thank you.